I want to start off talking about Turing tests. Here we have the Imitation Game. You saw the movie, I think, from 2014. We have scientists, Alan Turing, cracking the Enigma code and essentially changing, kind of turning the tides for nature war. And in here, there's this idea of a Turing test. Originally, Alan Turing called this the imitation game. Right now, it's known as a Turing test. How indistinguishable is the machine from a person? I want to talk a little bit about foundation models. One question, will a foundation model trained on simulation data lead to experimentally realized materials? Additionally, will a foundation model trained on literature data lead to discovery of novel, high-performing materials? Now, structure, which is a lot of the simulation bulk that's been out there, is much simpler usually to simulate than synthesis. So let's say you had 1,500 A100 GPUs at your disposal. How many atoms might you be able to simulate with this? Well, the answer is maybe about 10 to the 8th, keeping in mind that a grain of sand is 10 to the 20 atoms. And let's say you have an hour that you're running these 1,500 A100 GPUs on. How long could you run the simulation for? The answer is a few picoseconds. It's very difficult to model and simulate these processes that span time, and they span many different length scales. So many time scales, many length scales. Going to that second question, experimental literature is often sparse and very concentrated in certain regions. There's a study from 2019, and for these different chemical reaction pathways and conditions, they generated 500, they just randomly chose 500 experiments, and as in like randomly generated those parameters for it. And it turned out that the choices of reaction conditions were uncorrelated with success. And that the randomly generated experiments tended to better illustrate that range. To hit home, machine learning models that they trained on a very small randomized reaction data set outperformed ones trained on the entire human selected reaction data set. Now, these are obviously some like hand-picked examples, and I would say in many cases, the simulations, the literature data play a key role. We're now entering an age where combining AI and automation is accelerating the scientific discovery process, helping us improve efficiency, our time to results, and reproducibility. Here we have the world's brightest molecule discovered in this international collaboration, Nexus, University of Toronto. This is important for quantum research applications. We've seen some other examples like the discovery of higher performing, so stronger, more sustainable concrete, as well as the world's best shock absorber, which is important for you can think of like helmets or other shock absorption applications there. And when we think about these two aspects, AI is usually about maximizing the value of individual experiments. So this looks like reducing number of required experiments, choosing the ones with the most information gain, and oftentimes we're predicting properties and quantifying uncertainty. Automation, on the other hand, is all about minimizing the burden of individual experiments. So we're trying to reduce tedious manual steps, we're increasing reliability, repeatability, and we're trying to increase our speed and throughput. Now, a self-driving lab is a system that closes the loop of scientific discovery. We start out initializing some campaign, our high-level objectives, what our search space is. We suggest new experiments, we synthesize those materials, we test their performance, and we follow this in a loop until we reach some stopping criteria, which could very well be the end of a grant or students graduating, or you found the material that you were looking for. And fully self-driving labs are autonomous systems that can perform many iterations without human intervention. So similar to like self-driving cars and levels of automation there, what we're headed to as a community is these sort of level 4 self-driving laboratories, where we have full workflows automated over multiple iterations. Here we have an example of a self-driving laboratory that actually does some driving. Not all do. But here we have a dual-armed robot uncapping vials and passing it to a mobile manipulator, a robot arm on wheels, that takes the samples and brings them over to an X-ray diffraction machine to characterize powders. This is highly sped up, by the way. We make it over, it calibrates its position against this block, opens one door, opens the other door, calibrates again to be able to pick up the samples and insert them into the machine. Now, we must not forget that the doors are open, so we'll calibrate one more time, and we'll close one door, close the other door, at which point the characterization proceeds. Now, when people look at these kinds of self-driving labs, it can be pretty daunting, kind of like staring over the edge of a high dive. We, as the Acceleration Consortium, as a community, have also taken this focus on a frugal twin concept, kind of like a digital twin, but more on the cost fidelity research spectrum. So a frugal twin self-driving lab is a low-cost counterpart to a high-cost one. And this is really useful for education, for prototyping, and even multi-fidelity machine learning research. And so on the low-cost, low-fidelity spectrum, you might have this like mixing red, yellow, and blue food coloring or paint. And on the high end, you have a full liquid and powder handling setup with, fairly expensive characterization equipment and everything, everywhere in between. As one example, I would say my favorite example of a frugal twin self-driving lab is a PhD student who came and built a self-driving lab for discovering electrocatalysts, which is really important for green energy applications, in about 3 months for under $5,000, and then he replicated it when he went back to his home institution. You can see this in action here. So it's picking up different tooling. It's adding these metal precursors. It's grabbing a tool, the electrode, for doing electrode deposition, and then cleaning the electrode, and then carries this out iteratively in a loop. Now, we're also exploring the idea of cloud experimentation. So here we have a remote access demo. You'll enter an ID, sorts, verify it, and we have a YouTube live stream going on 24/7. So we'll set red, yellow, and blue volumes here, and we'll see on this live stream that after we hit submit experiment, it goes, it picks up the pipette tip, dispenses red, yellow, blue, and at the end it picks up this wireless color sensor tool to measure the color there. And we skipped a little bit here, but on the bottom left, it's we get that kind of color measurement data. And this kind of system can also be called programmatically with an API. And in a course, self-driving labs for materials taught by J. Hatrick Simpers this last semester, so there were about 18 students who accessed this piece of equipment remotely and asynchronously, and in total conducted well over 1,000 experiments on this. We're also exploring some novel ways to approach autonomy in the physical sciences. I'll posit that the future of self-driving labs is vertical. When we look at traditional laboratories, they're very space efficient often, but they usually lag in vertical space automation. So you look at a typical kind of lab casework, desk, trays, things like that, you get about an 8 times increase in area compared to the footprint. But the automation friendly of that is a 1-to-1, pretty much, just that desk space with nice overhead clearance. So we're taking kind of this example of inorganic solid state synthesis. You have some powder that you dispense, some kind of liquid handler, characterization tools, and testing for that. And this is what a traditional laboratory might look like, and this idea of putting a mobile manipulator there to pick up samples. When we look at a vertical self-driving lab, equipment comes to the operator instead. So we have some kind of operation table, storage in the front, storage in the back, and this elevator or lift that brings it equipment that stays powered on to a storage position and brings it back. So it's in storage. You are able to run experiments for hours or days. When you need to transfer, switch out a sample or do some maintenance on the equipment or have somebody use it manually, then you bring it back to its kind of operation table position. Now, these are real systems, and we're exploring embedding these into some of the laboratories here. So you can see here, we've got in the view of inside the machine, it's being raised and put into the storage position. You can kind of see at the top there. And when you call it back, second, it'll take it, bring it back out to the operation position. And one of the things I'm working towards is a vertical self-driving lab for autonomous alloy discovery. And at the Acceleration Consortium, we're building 7 core self-driving lab facilities that span all sorts of different domains: inorganic materials, organic small molecules, medicinal chemistry, polymer materials, formulations like shampoos or nanomedicines, looking at even this lab called human organ mimicry, so the synthesis of artificial organs and using those for drug testing. And then looking at scaling up these systems from gram scale synthesis to kilogram scale synthesis. Now, there are a number of algorithms that can help us to intelligently select the next experiment that we should run. We see this dramatic improvement when we go from traditional design of experiments to something that is adaptive experimentation, such as Bayesian optimization. And oftentimes the task looks like find the synthesis pathway that maximizes some property like binding affinity to a particular disease, or find the composition and processing parameters that maximizes, say, like alloy yield strength. And these generally involve, again, predicting properties, quantifying uncertainty. So if we have, in this case, a Gaussian process model, we have our noisy observations as the black points. We have our surrogate model with its prediction uncertainties in blue, and then our true model and our global optimum at the top. So we have our objective function, f of x, and we have one variable that we're tuning here. And we use an acquisition function to guide how to select the next experiment. You'll notice here that the acquisition function maximum is neither the max predicted value nor the max uncertainty. It's this trade-off between exploiting what we know to be good and exploring regions that we're uncertain about. And this gets carried out in a loop where we add data, refit our surrogate model, optimize the acquisition function, and we progressively reach our maximum. Now, real-world materials discovery tasks require more than just vanilla optimization. We have simulations and experiments that we're trying to unify. We have many performance properties that we're interested in and that have trade-offs with each other. There's usually a mix of continuous and categorical variable types. These are high-dimensional spaces. There are some unique constraints, like the fact that an alloy wouldn't have more than 6, 7, maybe 8 unique elements in it from a thermodynamic standpoint. And if we look at each of these on the left, so we have like single versus multitask, single versus multi-objective for each of these. And vanilla optimization would be this basic, everything on the left, whereas a more advanced one might be multi-objective, high-dimensional optimization. One of the tools that I worked with some others to create is called Honegumi, and this allows you to quickly generate minimal working examples for these advanced optimization tasks. So on the left, you have an example that's 21 lines. When you move to this more advanced tasks, you're tripling the number of lines of code for this minimal working example, and you're also changing how you're interacting with the API and the syntax there. And this is a structure that pairs really well with large language models, where you take, it's kind of like a prompt template, or like doing some prompt engineering and giving it a starting point for it. You can see that tool in operation here, where we can select, kind of toggle these different aspects for a number of different types. And if we get a little obnoxious and just turn everything to the more advanced state here, this template will dynamically and automatically populate kind of that full working example. Now, one of the reasons I bring this up is because if you're going to integrate graph neural networks, generative models, and other advanced topics, you really need to be able to leverage these advanced concepts and topics. And I've watched people, spend 6 months, 6 to 12 months in their PhD just trying to grapple with the syntax and the API and the concepts. And so this is a resource that can help a lot with that. There are many tutorials, both conceptual and hands-on here. Then for this next part, since I think we're at about 16 minutes already. A second.
Yeah, 4 minutes left of the slot.
Okay. I want to jump ahead and just talk about some of the challenges that we're facing when it comes to these advanced optimization topics. So here we have this idea of multitask optimization. We have two systems, maybe they're in separate laboratories, or maybe it's like a closely related material system. So we have task A and we have task B. Now, with multitask kernels and Bayesian optimization, one of the issues is that these often extrapolate to a common mean. So if you have our task A, task B, our measured data points in black, and then the model predictions, and then the dotted lines being the true functions, when we look at that extrapolation behavior, we notice that both models, so the solid blue, the solid gray, extrapolate to the common mean, but in reality, for materials problems, this is often not the case. We often don't know appropriate or like the right scaling to make this kind of shift in scaling to make this true. And so one of the things that we're building in the community is this idea of Turing test optimization benchmarks. Going back to here, so one thing I'm very interested in is designing optimization benchmarks that are nearly identical and indistinguishable from the real underlying function. And so this is one place where I can see foundation models trained on large simulated and experimental and literature-based data sets coming together to try to kind of pass this Turing test for optimization. And one of the things we're planning to do is host an optimization benchmarking competition on Kaggle. So if you're interested, please reach out. I'd love to collaborate on releasing some of those tasks. So here we're at the Acceleration Consortium. I encourage you to check out this link. It has some of the topics that I covered, different hands-on demos, as well as manuscripts. Thanks.